In this video, we're going to go into a little bit more depth on the field of quotients of an integral domain, and we're going to make some progress towards showing that it's a field. We're not going to prove all the properties of a field, because as you'll see momentarily, there are a lot of little things to prove, but we're going to talk about some of the major points. Okay, so I've put in here the definition of the field of quotients of an integral domain, just so that we have this on hand. Now let's think about what it would take to prove this is a field. So what would it take to prove f is a field? Well, we need to do the following things. We need to show that f is a ring. So in other words, we would need to show that addition and multiplication are well defined. And in fact, that they give us elements of f. And one thing that we didn't do in the last video was we didn't show when we add two of these classes together, when we add, for example, A1, B1, and A2, B2, that what we get actually is an element of f, because we didn't show, or we didn't say anything to indicate that this number here, or sorry, this element of D would be non-zero. But actually that follows from D being an integral domain. We're given that B1 and B2 are non-zero because these are ordered pairs belonging to S. And so when we multiply B1 and B2, we will still get something non-zero because we're in an integral domain. There's no zero divisors. Okay, so now that we got that out of the way, we're going to check that off. We've mostly shown that addition and multiplication are well defined. We showed it for addition, and the proof for multiplication is not too different. Okay, we need to show addition is associative. We need to show that there's an additive identity. We need to show each element has an additive inverse. We need to show that addition is commutative. We need to show that multiplication is associative. We need to show that there is a working distributive property. And I think those are the main points of showing that f is a ring. Now, to show that f is a field, we need to do a few additional things. We need to prove that the multiplication is commutative. We need to prove that there is a multiplicative identity, that is a unity. And we need to show that every non-zero element has a multiplicative inverse. And I think that's it. As long as we can prove these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things, we will have shown that f is a field. Okay, good news. We're not going to prove all 10 things in this video. Most of them are kind of tedious algebraic things to check. You work out an algebraic calculation, for example, that if I add 3 elements of this field, or this supposed field, it doesn't matter whether I group the first 2 or the last 2. That's something you could do on your own. But I do want to talk about where the additive identity comes from, where the multiplicative identity comes from, and also where inverses come from. Because I think those are really the most memorable parts in terms of us having to use this equivalence in clever ways to show that we actually have inverses that work. So I'm going to zoom this out, and we're going to prove just a few of these properties. There we go. So let's start with the fact that there is an additive identity. We're going to take the fact of addition being associative and commutative for granted for now. All right, where are we going to find an additive identity in this set? Well, if we think of A comma B, the ordered pair A comma B is representing a fraction A over B. What do we think would be a fraction that would represent 0 in this number system? Well, certainly something like this ought to work. I mean, we want something that's expressed as a fraction. We can't just say 0 and have that be the end of it. We need an ordered pair. But what if we try the ordered pair that represents 0, 1? So 0, 1. By the way, I realize that we're not working in an integral domain that necessarily has actual integers in it. So when I say 0, 1, I don't mean the numbers 0 and 1. I mean whatever is the additive identity of D, and I mean whatever is the unity of D, because we're assuming integral domain, therefore we have a unity. Okay, so we'll show the class of 0, 1, and we're just going to try and remember that this represents an element of D and this represents an element of D, that this is an additive identity for f. Okay? To show this, we're going to let a comma b be some other element of f. And we're going to try adding. So then we get ab plus 0, 1. And using our formula for addition, which is given as part of the definition of f, we're going to get a1 plus 0b, comma, b1. And what does that work out to? Well, a times 1 is a, 0 times b is 0. So we get a, comma, b. Okay, so that's great. So 0, 1 really does act as an additive identity. And we're assuming that we've already proven that addition is commutative, so we're going to assume that the other addition works out as well. Okay, so we have an additive identity for f, but what about a multiplicative identity? What would work well there? Well, we found an additive identity by thinking about what we know about fractions and the fact that 0 is representable as a fraction. And when we think multiplicative identity, we think of the number 1. But how do we represent 1 as a fraction? Well, we usually think that's 1 over 1, and then we can represent that as the ordered pair 1, 1. And again, that's the unity in our integral domain D. So we'll show, or at least we hope we'll show, that 1, 1, the class of that is a multiplicative identity for f. All right, to show this, let's let AB be an element of f. Okay, then what happens if we multiply? AB 1, 1 is equal to the class of A1, B1, and of course that works out perfectly to be AB. Okay, so we're good there. We have a multiplicative identity. Now let's switch colors because we're going to do something different now. We're going to try and find inverses. So let's let AB be an element of f. What do we think would work as an additive inverse of AB? So again, we think of this as being like the fraction a over b. And think about what fraction you would create that we could add to this to give 0. The first thing you might think of is negative a over b, but I need something that's expressible as an ordered pair, and I don't know where to put that negative sign in an ordered pair. Or, well, do I? Because I could always move that negative sign up and express the fraction that way. So let's try doing that. We'll show negative AB is an additive inverse for AB. Okay, so let's try adding them up. Now this one, you may think this is going to be another boring calculation, but something interesting is going to happen this time that we're going to have to sort out. So this time when we use our formula to add, we get AB plus negative AB, comma, B times B. And that's going to be a B squared. I'll just write it that way for now. And by basic properties of additive inverses for rings, we know that that works out to AB plus negative AB. That's the same thing by a theorem that we have, and that's B squared in the denominator there. Okay, so that works out to 0b squared, but we did not say that 0b squared was the additive identity. We said that 0, 1 was the additive identity. Okay, but wait a minute. This is sort of like the fraction 0 over 1, and this is like 0 over b squared. Are those really different? And the answer is no. We know that 0b squared is equivalent to 0, 1 because we can cross multiply and verify that. So we multiply, and let me use my little spotlight here so you can see what I'm multiplying. 0 times 1 is equal to 0 times b squared. Both of those are equal to 0. Okay, so we can say that this is equivalent to the class of 0, 1. In fact, it's the same class. And that's the additive identity. So yes, this really is an additive inverse. Okay, what about multiplicative inverses? Okay, let's let AB belong to F. Okay, but one more thing. We need to assume it's non-zero. We don't expect to find a multiplicative inverse of 0. So let's assume this is a non-zero element of F. Then what can we say about A and B? What we'd really like to be able to say is that A is non-zero, but is that true? Okay, well, let's check. So we claim A is non-zero. Okay, and this is true because if A were 0, then we'd have AB equivalent to 0, 1, since A1 would be equal to 0B, since A is 0. Okay, and that would contradict AB being non-zero. Okay, so that means that A has to be non-zero, which is good news because the way we're going to find a multiplicative inverse is pretty much the way that you would expect if we were thinking about fractions. I mean, the ordered pair AB represents the fraction A over B. And, well, how do we expect to find a multiplicative inverse for A over B? Well, we think, okay, how about B over A? And then we look at the ordered pair B comma A. But we only get to do this because we know that A is non-zero. If A were equal to 0, then I couldn't even talk about this ordered pair belonging to F, or its class belonging to F. So that's why this is really crucial. Okay, so anyway, so we'll show this is a multiplicative inverse for the class of AB. And again, this is a pretty straightforward verification because if I multiply the two, I get AB times BA, and that gives me AB. I guess really technically I have AB, BA, but multiplication in D is commutative. It's an integral domain. And that's equal to the class of 1, 1. This is true since, there we go, since AB1 is equal to 1 AB. I'm just cross-multiplying to show those are equivalent. All right, so that means the product of these two is the multiplicative identity, which we said was 1, 1. Therefore, AB has an inverse. Hooray. So what we've just proven is that this thing we've invented, this thing we're calling the field of quotients, actually does have a lot of the necessary ingredients to be a ring. It has an additive identity. Every element has an additive inverse. It has a multiplicative identity. We found that up here. And also has a multiplicative inverse for every non-zero element. We did not prove all the other properties, but I claim that the other ones can be proven using pretty routine calculations and occasionally clever use of the equivalence definition here, this equivalence relation tilde. Sometimes we need that to show that the results of two different calculations, even though they don't look exactly the same, they do represent the same equivalence class. Okay, so now just a brief note on why we would care to do this, because we're not going to have much time in this course to develop this idea further, but I actually claim this is a really important idea. All right, so one fact about this field of quotients. F contains a subring isomorphic to the original integral domain. Okay, and well, where do we find it? Because F doesn't actually contain the elements of D, it contains ordered pairs, or rather equivalence classes of ordered pairs. So you might wonder, where are we actually going to find the elements of D in this field? Well, we can define a map from D to F that tells you where to locate each element of D inside of this field. Okay, and the way that we do that is we say, okay, phi of x for each x in the domain, phi of x is equal to the class containing the ordered pair, and I'm pausing because I want you to think about what element of f we might identify with this element x. Like, really what we're asking here is, how do we think of x, an element of the original integral domain, as a fraction? Well, we think of it as x over 1. So that's where we locate x. So phi of x is going to be defined to be the class of x comma 1. And you can prove, even though we're not going to do it in this video, that this is a ring homomorphism. It preserves addition and preserves multiplication. It is 1-to-1. It's just not necessarily onto. It won't necessarily be onto f. Although if D is a field, it actually will be, which is kind of a fun fact. Okay, but why do we care that f contains a subring isomorphic to D? Why do we care that we can build a homomorphism, an injective homomorphism from D into f? Well, the reason we care about that is that once we have that in place, we think of this not just as some weird, random, arbitrary construction that we do with an integral domain to create a brand new ring. This is actually a way of extending D, extending an integral domain into a bigger ring that contains multiplicative inverses. So we're building from an integral domain a field that contains it, which is kind of cool. All right, so for example, like where would we do this? Because we kind of didn't need this construction to be able to think about the rational numbers. We have an idea from grade school of what the rational numbers are. So we didn't need this construction to create those. But if we have, suppose we have an integral domain D and construct the ring of polynomials D bracket x. So again, that's the ring of polynomials whose coefficients come from D. Well then, the field of quotients of D bracket x, well, what is that going to have in it? Well, a typical element is going to look like this. It's going to be an equivalence class of some ordered pair, but the ordered pair contains a polynomial followed by another polynomial. Sorry, that's so small there. But we think of that as being representative of this rational function. So the field of quotients is really this other thing that we call D parentheses x, which is the field of rational functions over D. In other words, rational functions having coefficients from this integral domain. And we will learn more about those in the next course.